to go quickly. This is a class I usually give in 3 hours. I'll skip the calculation, or many of the calculations, but they're in the notes. Okay, so let me start by saying we did yesterday the linear stability analysis of Rayleigh-Bernard convection. Remember we got that wave number Q, which was, I think for the pre-slip case, what was it? It was 1 over square root of 2 or something square root of 2, something, I don't know, I'm not good with numbers. And for the rigid boundaries, it was pi. And you remember I said that corresponded to straight, to round rolls. So now you know about, and you know we did that calculation. So you know that you can find critical wave numbers. You may also remember that we imposed a functional form sine qx, periodic stripes, right? Okay. But actually, we didn't really have to do that. We could have said e to the I q dot x, where remember I said that it would be independent of y, the y direction. But it could have been independent. It could have been just any direction. We could have waves going, the wave vector q in any direction, right? Okay. So what is our eigenvectors look like e to the I q dot x here, because the horizontal surface was homogeneous. Homogeneous here, meaning that there is no distinguished location in the horizontal plane. We have put no boundaries to say, oh, we're close to the boundaries, we're far from the boundaries. We have put no tilt to say, oh, we're going this way, not going down, not going up. It's homogeneous in the plane. You remember that from convection there. And that leads to the result that necessarily, remember I said I didn't like so much this word ansatz, as if it was a guess, a lucky guess. No, it's a mathematical truth that the eigenvectors must be of the form e to the I q dot x. This is linear, for linear stability analysis gives you a linear system of equations with constant coefficients. The eigenvectors are homogeneous in the horizontal plane. The eigenvectors are necessarily from e to the I q dot x, and we figured out what q was. But we did not figure out any direction for q. Q was, I had said, we're going to ignore y, and so our q just multiplied x. We had sine qx. And we see, of course, now it could have been in any direction. So you might say that's trivial, that it could be in any direction. Of course it could be in any direction. You could have your rolls here, or here, or here. Since the horizontal plane is infinite, of course it could be in any direction. But that's not the point. The point is that you have a circle's worth of possible orientations, and your final solution could be a superposition of e to the I q dot x with different orientations. So you don't necessarily have solutions that are just straight like that. You could sum this with this, right? Or not. Who knows? And that's kind of what this class is about. What is it finally going to look like if it's not going to look like stripes? Or even if it is going to look like stripes, what does the pattern look like? Okay, so indeed I said that near threshold we found eigenvectors, and the new solution is approximately a sum coefficients of the eigenvectors. What are the coefficients? Are they what is allowed? So that's again what this class is about. Linearly, I think I was speaking with somebody about this at some meal. Of course, you can just superpose. If this is an eigenvector and this is an eigenvector, then their sum is an eigenvector. Any sum is an eigenvector, right? So you have a tremendous number of eigenvectors. What finally decides the solution are the nonlinear terms. There are principles, that very general principles that apply to all systems. They're a result of the mathematics of symmetry, so equivariant bifurcation theory. The nonlinear terms are going to determine what is allowed with the relative magnitudes of BQ. Not only the magnitudes, but the relative magnitudes. And this is a unfinished field. We spoke yesterday, I think, about square patterns, hexagonal patterns, which is what I'm going to talk about this time. But the mathematics does not yet know how to choose between squares and hexagons. There is no mathematics that tells you from the equations, or from even simple equations, whether you're going to get squares or hexagons. You can determine whether you're going to get squares. You have to set a lattice, so you can determine whether you're going to get squares or rolls. Because once you set your lattice, a square lattice, you could have something like this, or you could just have something like this, or something like this, or you could have a hexagonal lattice, right? And then you can get hexagons, or again, rolls in some direction. But the mathematics does not yet exist for deciding between all possible patterns. And, I'm sorry, just one moment, somebody asked yesterday about the free energy and stuff, and there is no energy deciding what, there's nothing that we can calculate that is going to, when we look at the stripes, what's the energy rectangles, what's the energy hex squares, what's the energy, so, and we choose the minimum energy solution. There is no such principle. Yes?
I was just curious, I mean, this question, this problem that you just discussed, has been an unsolved problem for a very long time, right?
So,
So do you think it's ever going to be solved?
oh.
I was just curious.
Oh,
Seriously, I mean,
okay,
is there a
yes,
hope?
yes, yes.
Or is
Okay.
this just like miserable?
It may have been an unsolved problem, but I taught, I teach this a lot, and it is amazing how, for such a simple field, how everything was done in the 1980s.
Exactly.
Things that could have been done, it's not, things that could have been done.
But this problem has existed since the 70s or 80s, right, or wherever. Because people have known you don't know how to do this for a long time.
Oh, well, I wouldn't say that's that long.
Well,
I said that yesterday, didn't we? I'm older than you are. I'm older than you are.
But I guess I'm just curious, because you thought about this for a long time. You thought about this first.
Oh, no, but I
anyone in the room.
I'm a consumer of this theory, not a
You thought
producer.
about it more than anyone in the room.
Maybe.
I think it's true. So, but, I mean, do you think, is this one of these problems that you think?
No, I think it'll, okay, all right, I should say, I don't know enough to really know the answer to your question. I don't know how hard it is. I just one of my facts, the way I tell, that's not solved. But I don't know, I don't have enough, I'm not the kind of person who proves these kind of theorems, so I can't say.
No, it's not a theorem thing, it's just figuring out what happens then. Anyway.
Okay, so let's start by deriving the Swift-Hohenberg equation. Probably many of you have heard of it. How many of you have heard of the Swift-Hohenberg equation? How many have not heard of the Swift-Hohenberg equation? Okay, let's do that again. How many have heard of the Swift-Hohenberg equation? Good. How many have not? Okay, it's getting to be 100%. Good. Okay, so this is a kind of general equation that describes a lot of pattern formation. So I'm going to drive it very quickly. We just spoke here about e to the I q dot x, the wave number q, and you may remember from last class. Boy, yeah, I was wondering yesterday whether I should do anything as specific as convection, but I see I really do need a source of examples. You remember, how did we find the threshold, the critical Rayleigh number? We found it by we found a lambda. We looked for an eigenvalue when it was 0. And what was that eigenvalue? I called it lambda, maybe I should have called it sigma. It was a growth rate. It came from the d by dt. You may recall I had e to the lambda t, and then I had lambda. So lambda was a function of q. Sigma. So these are the growth rates, sigma, of perturbations, eigenvectors of that form. Okay, and maybe just to recall, maybe I'll just put that up. Yeah. Yeah, you recall we had this matrix wave, this lambda that was a growth rate for perturbations with the wave number q. Q, and we had e to the lambda t. Okay. Let us now. Okay, but this we did from Boussinesq equations. So let's start from the whole PDE is three-dimensional with the Boussinesq approximation, non-dimensionalization to stream function. We went all the way down from the full equations, and we built up to this very simple little 2x2 matrix. Now we're going to do the opposite. We're just going to think, oh, what would I like? What would I like? I'm just going to make this up. I'm not thinking about negative strips. I'm not thinking about anything. I'm going to choose sigma as I wish. So what do I want from it? Well, I want it to only depend on q squared. That is to say, I want it to be an analytic function. So, first of all, I only want it to depend on the magnitude of q. We already said that. It shouldn't matter for the homogeneous surface whether the rolls point this way or this way. It better depend only on the magnitude of q and not on its orientation. But in addition, I don't want it to be a function of q like that, of the magnitude, because that's not an analytic function. So I want it to depend on q squared. Q squared being q dot q, right? Q dot q. Okay. I want there to be a critical wave number. I don't want to allow, remember I drew this last time, I don't want to allow rolls of, I want it to be, remember the different q's corresponding to things like this? So I want there to be, I want the sigma to depend on Q. I want there to be some preferred value, which last time was like two rows like that, right, circular rows. I want there to be some preferred value, QC, and I want sigma to be positive for Q greater than QC, and I don't want, I certainly want it to be, I want perturbations arbitrarily large wave number like this to be damped. Okay, so the simplest function I can make that satisfies all that is a Bordic function like this. Okay? Okay, so now I've drawn it. This is the simplest function. I haven't, you know, if I pick, this is the simplest function that will satisfy all those properties. Okay, so this is a growth rate, and it's positive for QC. Here I've chosen 1. Okay, and it's negative far enough away. And it depends, and it's even in Q, it depends only on Q squared. Okay? Yes? Are you going to tell me that's not true, that there's another function C? No? Okay.
So, why the growth rate has to be analytic?
I don't know. I don't know. Like it that way. Okay, it's derived from partial differential equation. Okay, if I was a real mathematician, I would know stuff about, I would be able to answer both ways. That is to say, I would know about partial differential equations that were kind of pathological, where you only needed things to be, you know, C3 instead of C infinity, and I would know about all those cases, just how strong you had to be, and I would also, to me, not being like that, to me all good functions are analytic, because I'm an amateur. Is that an answer? So, okay, maybe a better answer is, I don't know. Other question? Okay, so here we have sigma that I just wrote down here, and here's my next step. Sigma, I'm going to turn into d by dt. You remember how that happened? We have e to the sigma t, so that's d by dt. And q squared, that's going to be the Laplacian, right? E to the iq dot x, you take the Laplacian, and what happens here is you bring down a q squared. So I'm going to turn my algebraic equation into a partial differential equation, not even a differential, but partial, where I had the same, I'm going to write d by dt, where I had, and this expression here, this stays a scalar here, and then I'm going to have the Laplacian. And now, we don't just want a growth rate like this, because although here, indeed, we satisfy the property that sigma is negative for q sufficiently large. For q in here, it is positive, meaning that in time, if this was your parameter you were looking at, q, you're looking for growth of, or decay of perturbations with this q, they're going to grow forever. E to the sigma t is positive and growing, and grow forever. So you need a saturating term, and that's here. That's to say, this u, without this term, for q, near qc, this would grow forever in time. Exponential growth with this sigma. But this is a saturating nonlinearity. This is the simplest saturating nonlinearity you can have. You might say, now here I do sort of have an answer. You might say, well, the simplest, why cubic? Why not say quadratic or something? And that is something that we will discuss later. And what am I going to do now? No, I'm not going to do this. As nice as that is, I am going to, you may notice I cleared my, but it's not the text, it's not the text. I'll show you. It's that I was using the wrong software to show you this. Okay, so these are, this is an invaluable resource. This is my Michael Cross from Caltech, part of course of pattern formation. He made some Java applets that simulate these equations, and so I think they're wonderful. And here is a simulation of this Newton-Holmberg equation, starting from this initial condition. Let's let it go. Okay, so it forms stripes. That's nice. Okay, now we can, let's reset it. And now, this is sort of a noisy initial condition. Let's look instead in the Fourier space. We'll look at the Fourier transform of that solution. So what does that mean? Okay, you saw, okay, hold on. Let's look at this solution here. Can we do that? can't see it in the screen. Okay, this is the Q space, this Q here. So this is QX and QY. And you saw how quickly it settled down immediately to a ring. A ring meaning the right value of Q, the magnitude of Q. The orientation it didn't choose, but the magnitude it chose very quickly. Let's do that again. This is a noisy condition in Fourier space. Think right away a ring. And now it thinks about it, and finally it's going to form. Now, okay, what this means is this is a Q and a minus Q. Because obviously our solutions can't really look like e to the I q dot x. That would be complex. They're e to the I q dot x plus complex conjugate times e to the minus q dot x. And let's see, okay, stop. Let's look at this. Why can't I look at this? I have to see it in. Let's see. There, okay, right, so it strikes like that. So just as I was showing you a wave vector, you see this wave vector is like this, and that corresponds to Q like this, plus Q minus Q, okay? And let's do it just one more time. Restart. There, this is what I want to see. You see there are defects. Right away it went to the right lane, but then it had defects. That's the slow part. Right away it went to, it's different every time because it's random initial conditions. So right away it does the stripes, but at the very end then it does that thing where it can't decide on the orientation. It wants to be stripes everywhere, but it has a little hard time at the end. Okay? And that's the Swift-Hohenberg equation that we just made up starting from those general principles. Okay, while I'm here, let me show you some other things from this. Yes, okay, so that was the Swift-Hohenberg equation. You can recognize it here. This is what I call mu. The psi is what I call u. The QC is 1. So you see it's just the equation that I set up here. There's a saturating cubic term, but there is a quadratic term, which I said I would talk about. Not so much now, but a little later. So, and that's what this G1 is. So there hasn't been a quadratic term. Let us do a simulation with a quadratic term. You see the G1 is 1 here. And let's start it. So it form hexagons. And we will learn, I hope if we get to it today, what that quadratic term has to do with having hexagons. Okay, we can again do this in the Fourier space. Okay, first let's here, you see we have 6 wave vectors. 6 spread around the unit circle like that. There's 3, and then they're complex conjugates. We can do it again. We can do this in Fourier space now. Right away it goes to a ring. That it does really quickly. But now it still has a little trouble. Okay, hold on, let's see. What does it look like? Yes, you see it's hexagons, but not quite finished. There's this thing here, this thing here. It's kind of fighting. And here, okay, finally it gets down there. So it's first it forms a ring that's really fast, and then the rest is trying to get the defects. You can even, let's see, what's this? This is just a bigger, thinner system. That's fun. It's going to form stripes, but it has more room to make these defects. Again, we can look in Fourier space. It's a ring, but it's not striped. It's going to form, you can see it's going to form rolls here, but it's not finished yet. You see, it has this orientation, but it also has this orientation, and you can see that, here. It has this orientation, but it also has this orientation, and I think you'll find that that does correspond to this orientation and this orientation Q. Okay? And it'll take a while. Let's continue. Now this looks like the Swift-Hohenberg equation, but it's got another term like this. It's got this one here, instead of QC, is just a choice of length scales. It's got another term here. So there's a one that's length scale, and another one that they've called Q here. And there's a quadratic term and a cubic term. Okay, and let's see what happens here. Okay, so you see it. You see two length scales, one like this and one like this. The little one and the big one. Right? This is Q of 1.9. That 2 pi over Q is probably this, and then the Q of 1, and that's this, or else the other way around. Sorry, I get mixed up. Okay, and that's a quasi-pattern. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? Little guys going around the top one. It's not a perfect tiling because such things do not tile a plane. We can look at it in the Fourier space. And you see, you have, this is the, one of them is 1 and 1. This is 1, and this is the Q, which is about 2. And again, you can see it evolve in the Fourier space. Right away it forms 2 rings, but it's not yet decided about, oh no, yeah, that's pretty good. Okay, so Swift-Hornburn equation does all these things, and this is very discouraging for me because I spent most of my career, until pretty recently, writing huge hydrodynamic codes to solve real Navier-Stokes and real Boussinesq equations, and this little equation, you know, we can program it in about a week, 2 weeks, and it does most things.
But you don't get the numbers yet.
Yeah. Thank you. That helps. Okay, so this is my still slide of what...
This was meant as an encouraging comment.
No, I knew it was. I knew it was. My tone did not. My tone was.
It's important to get
Right.
that.
My tone was that it was.
Brewster was not very happy probably with Swift-Hornburn equation.
I'm sorry.
Brewster.
Brewster.
Who you
Yes,
talk about,
yes.
he's not very happy about
Yes,
Swift-Hornburn
yes,
equation
yes,
either.
yes. For the same kind of reasons, we tried to get it right. Well, it's true. You need the truth to make sure that this is right. At any rate, so but enough about about me. Let's go back to class here. Okay, so let me just continue a little tiny bit with the equation. You saw before that that growth rate, the sigma. Now what we're looking at here is the okay. This is what's called a neutral curve. What's a neutral curve? It is okay. This is what we did last time. As I said, we're looking for when d by dt is 0, when the perturbation neither grows nor decays. The dividing line between growth and decay. So we set 0 here, and this would just substitute q here. So we're looking for solutions to this. And this is the mu value. Mu you can think of as the Rayleigh number, the Reynolds number. This mu is the value of Rayleigh number, Reynolds number, at which perturbations with this wave number q become unstable. So for mu above this, you're unstable. For mu below this, you're stable. Again, what you'd really like to do, for mu very small, you're unstable to the nice wave number q. But if you really are mean to your system and you keep it from doing this, it will eventually, for a much higher mu, do something with a smaller q like that, or something with a larger q like this. It will, if you really keep it from doing this, and you raise your Rayleigh number really, really high, I don't know how you're going to keep it from doing this, but experimentalists think of clever things, it will eventually do this. So that's what's called the neutral curve. Here, I've shown a bifurcation diagram, meaning this is when it becomes unstable, but that's not the whole story. What we want also is the value of u. Remember I told you that this would just grow forever. This is e to the, or decay forever. It's just an exponential. I'll just start here. It's just a linear growth, that is to say exponential, and a linear differential equation leading to exponential growth or decay. But the cubic term is going to dictate its final magnitude, and this magnitude u is shown as a function of mu. So and these are different branches, meaning things associated to different q's. That is to say, things like this, or like this, or like this. So this one bifurcates first as you're raising mu. That's how you should think of it, just like the convection. You're raising the Rayleigh number. We start here, we become unstable to this, and then we saturate as we stop growing at this value of uq, and this is that branch here. The next one to become unstable as you raise mu is this one, and this creates a branch which exists for all values of mu above that value, and here it is. And then there are two that have almost the same mu threshold. They're right on top of each other here. And then there's another one, and that one's here, and then another one here that's here. Okay, and what dictates these little dots, this is a discretization. That's to say, this is an approach that I favor. This is very, this is not, most things I've been telling you are mainstream. This is not mainstream. This is my thing. In order to think properly in bifurcation theory terms, you want to have a discrete spectrum, meaning not a continuum of cues, and that is normal. You have, although I said you have an infinite plane, let us make it, keep it homogeneous. We're going to make it periodic, so you have to have a integer number, or you have to have your cue that fits into your box. Even though you're not going to introduce any discontinuities by making a wall, you're going to force it to be periodic, and that quantizes your cue. And that's what I do here, these cues are multiples of 2 pi over L. Okay, they're what fit into the box. Okay, and that's how I, okay. And for a particular length, as I said, of 24, and the QC that I used was the one for convection of pi, or maybe it was square root of 2. Anyway, the one was square root of 2, the one for free slips. Okay. Okay, so for those of you who read the, okay, I wanted you guys to read the notes that do about bifurcation diagrams, but anyway, you know about them now. And the other thing I wanted to say was, with periodic boundary conditions, you get circle pitchforks, meaning that the phase is undetermined. You could have rolls like this, or rolls whose origin is here, or here, or here, or here, or here. And you have a whole, so the phase can be anything from 0 to 2 pi, so you have a circle's worth of solutions that are just rolls, and that's called a circle pitchfork. If instead you impose Neumann boundary conditions, so it's not really homogeneous, but it's a subset of those periodic boundary conditions, it's still no discontinuity, then you'll get an ordinary pitchfork, meaning 2 solutions, something that you can have your solution that looks like this, or a solution that looks like this. And that is a pitchfork, meaning you can have one like this or one like this. And that's what you were seeing over here. That's why there were 2 solutions. This one goes one way, this one goes the other way. If you have periodicity rather than Neumann boundary conditions, then not only is this allowed, but even something like this is allowed, because this is not a wall in the case of periodic boundary conditions, or even something like. So that's, there you can have a circle's worth of solution. This is a circle's worth of solutions as a function of okay, so now we're going to go to, we'll finish the moment with the Swift-Hornberg equation. We will return to it later, I hope. We are now going to study square patterns. We're not going to think anymore about having different cues. I just said that I discretized a large domain by having long periodic boundaries. The other approach is to just have a small box so that really, you see how this guy is really far away. We can just have a small box so we're only considering a single wave number. We're not going to think about how they compete. Instead, we're going to think about this first question that I wrote here, which is superposition of cues with different orientations. We're not going to think about different magnitudes of Q, just different orientations. The simplest thing to think about is the square. So we have a periodicity which is merely the size of the preferred wave number like this. So all we're thinking about is the direction of our moves. Okay. So we have eigenvectors. As I said, our eigenvectors can have any orientation. But, and this is also what we were saying in the discussion with Michael, there is as yet not really much of a technology for dealing with any orientation, not in the way that we want to do, not the kind of technology that we want to use here. So we put on a square grid, and we restrict ourselves to the space of functions that are sums of waves in this direction and waves in this direction, trigonometric in this direction and trigonometric in that direction. Okay, we're going to look at something that's a sum of this with wave vector like this, and something that's like this with wave vector like that. Okay, so this is my x1 direction, and this is my x2 direction. Okay? So is everybody happy that, does everybody understand what I've done? I've just written a functional form, that's all. I haven't said anything about how it behaves. Surely I'm allowed to do this. Okay, and when I write this complex number, all that does is set an amplitude and phase. I could also write it as cosine and sine. and I have the complex conjugate so that I can make sure this is something realizable like a velocity field or a temperature field. Okay, now, if we learned equivariant bifurcation theory probably by the third class, you'd be able to derive that this is necessarily the most general cubic order equation that goes along with this. Yes?
What does the word equivariant mean?
What does it mean? Yes, it means conforming with the symmetries. Conforming with the symmetries. Okay, so these are the equations. Let me say a couple things about them rather than just bring them to this fact. I said that they were cubic order because we just want to stop there, and that's the simple. They don't have any quadratic term for reasons that I'm not going to discuss. What I do want to discuss is these parameters. They are the same. There's mu here and there's A. A is the self-saturating term. Remember I said we do minus U cubed to keep the growth from going on forever. When it gets big enough, the minus U cubed makes it stop growing, and so you have something stationary. Okay, so this is minus Z1 cubed. That's the self-saturated, how Z1 saturates itself, but Z2 also saturates Z1. This is the cross-saturating term. And I'm assuming that it's indifferent between this direction and this direction, and that means that these mu's are the same in these directions for these two, and that the self-saturating term here is one is the same as the self-saturating term for 2, and the cross-saturating term is the same. Okay, so you can see that these equations you could interchange Z1 and Z2. You see there I said Z. Who was talking about the fact that I said Z, unlike other Americans. Anyway, so we can interchange 1 and 2. Here, you can see the nonlinear terms. What dictates that it's cubic terms? Now I think I can tell you. Basically, it's the fact that this cubic term here, Z1 times Z1 bar times Z1 here. There, I'm multiplying with my Z's if I says Z1 times Z1 bar times Z1 here. That's going to go along to e to the ix1 times e to the minus ix1, the complex conjugate, times e to the ix1, the non-complex conjugate. And if you do that multiplication, you just get e to the ix1. And that's what says that this term is permitted. You can also do e to the ix2 times e to the minus ix2, the complex conjugate, times e to the ix1. And so that gives you x2 minus x2 plus x1, which would also be of that form. And that tells you that these terms are allowed, the nonlinear terms in this equation. And that you can't do it with quadratic terms. You can see that e to the ix1 times e to the ix1 gives you e to the 2ix1, and that's not e to the ix1. E to the ix1 times e to the minus ix1 gives you e to the i0, and that's not e to the ix1. E to the ix1, e to the ix2 gives you x1 plus x2. Anyway, none of them are going to give you these terms except for this. And finally, we're going to stop having these complex ones because we're just going to choose our origin. We can choose a phase for in the x direction and y direction, so we're going to make them real. So I said you would need a course of bifurcation theory, but no, in fact, I just did it here. This is what. This is why this is the most general equation compatible with these principles. And you're going to ask me some difficult question again? No, not yet. Okay. There. Okay, so we can look for steady states of these governing equations by putting 0 here. Before there was a d by dt, you may remember. And I like this way of solving equations. Okay. So we need to be steady, we need for Z1 not to move and Z2 not to move. That's to say we need this to be 0 and this to be 0. Both of these are factorizable. For this to be 0, either R1 is 0 or R1, R2 are on an ellipse.
R1 is the magnitude of Z1?
Sorry?
R1 is the magnitude of Z1?
Is the magnitude of Z1, yes, yes. Right. Yeah. So either R1 is 0 or R1, R2 lie on this ellipse. And to satisfy the second equation, either R2 is 0 or R1, R2 lie on this different ellipse. Naturally, these ellipses are empty for mu negative. Right? Okay, so for mu negative, you have no choice. The only solution, the only way to satisfy these is to have R1 equals 0, R2 equals 0. But for mu positive, if you can be on one of these ellipses, but you can't just be on one of the ellipses, either you've got to satisfy this and this, or this and this, or this and this, or this and this. That is, and I've drawn these in red and blue. That is to say, you've got to be on a red curve and on a blue curve. Okay, the red curves come from one, and one of these. So everything that's a solution is an intersection of red and blue. So for example, here this is R2 equals 0, and then this other ellipse here. Well, anyway, you get it. You have both. I've drawn both a line and an ellipse, and you have to intersect. So your solution's going to be intersected. And you see that you have four kinds of intersections. You have the origin, as I said before, that's this and this. Then you have on the axes. This is where R2 is equal to 0, but you're on this ellipse here. So this red is this ellipse. Or you have, so that's one kind, and then you have another kind that's on the axis here. So you have the x's, which are the trivial state 0. You have the circles, which are the just have x1. Actually, they just have r1, and r1. Let me remind you, I'm getting lost. R1 is the magnitude of x of z1, and r1, and so it's a magnitude of a functional form e to the ix1. So I'm talking about having functional form e to the ix1. I'm talking about something like this. This is e to the ix1, and r1 is the magnitude of that functional form. It's multiplied by this. Or I can have one that's r2, and that means I have something of the form e to the ix2, so that's like this. So I'm describing here 0, or rolls like this. That's the circles, or rolls like this, that's the triangles, or now that you can have the two ellipses that intersect one another, you're satisfying this and this, and that's these empty, squares? No, circles. Okay, circles. Oh, I know, of course. This is a circle, but I should use a different symbol. Right, these are squares. These are squares, that's to say they're a superposition of x1 and x2. That's why they're squares. But yeah, I should definitely have chosen that. Okay, and you can easily find the magnitude just from these obvious equations. Okay, so it's all very easy. Now we have to continue. Okay, let's first describe the square patterns. We said that we had to have this. This is the solution here. We have to have, and this goes back to I think what you said before. About traveling waves, standing waves, the equal superposition. I said I would answer that, and that's what I'm in the process of getting to. So you see that these are the only possible. Just algebra tells you that these are the only solutions, right? You cannot. This is again an illustration of the fact that at the linear stage, which was just here, you could have any magnitude for z1 and any magnitude for z2, right? But once you put in the nonlinearities, it's going to definitely select what you have. Okay, let's look at these squares just out of interest here. They're of this form. We have R every place. Instead of Z1 and Z2 or R1 and R2, we just have R. And we look at the functional form. We make these complex things real. They're sum of two cosines, which we can rewrite as a product of two cosines of the sum of the difference. We look for the nodal lines, and the nodal lines of this are when x1 equals minus x2, or when x1 equals x2 plus 2n pi. Right? The argument of the cosine has to be a okay. And so, in fact, the nodal lines, like the square pattern looks like that, which is a little bit unintuitive. You expect that if you add this and this, or maybe, I don't know, maybe your intuition is better than mine. You expect that if you add this and this, you're going to get something that looks like this. But no, you don't get something that looks like this. You get something that's at right angles to it. Not the right angles, 45 degrees to it. Okay. How many people found this intuitive or knew this already? Okay, how many people did not? Okay, okay. Here I'm not checking your nod. I'm checking intuition. I thought some of you have been with me during these past couple days, and I've asked people to find my way around because I have a very bad sense of direction. Now I can find my way, but at first I was really afraid of getting lost. And I thought maybe that has something to do with the fact that I can't, that to me this plus this is this, and so that's just, anybody with any normal sense of direction would know that of course it would look like this. So I'm relieved to see that that's not correlated. Okay, so now we see what our solutions look like. But now what we want to do is see which one is realized, which one is stable. Okay, so for those of you who read the dynamical systems handout, but I can go through it. Not. Okay, we talked before about a growth rate, which we call varies with lambda and sigma. But we have here not one equation, but two. We have two equations. So we could have several growth rates. And you might say, oh, well, we have only a single mu, so that not so, but you'll see we do. So what do we do when, in this case, when we have two evolution equations, or several evolution equations, we write down the Jacobian. The Jacobian is this. It's the derivative of the right-hand side with respect to R1, the derivative of the right-hand side with respect to R2, the derivative of the second right-hand side with respect to R1, the derivative of the second right-hand side. So it's a matrix of all the partial derivatives of these two functions. 2 by 2 matrix. So that's what it is in general. We can evaluate for this particular functional form, and this is what we get, this 2 by 2 matrix. You see that it depends, of course, on the parameters A and B and mu, but it also depends on R1 and R2. Just as a derivative, as you know, when we say f and we have f prime, we write f of x, and f prime of x, the value of the derivative depends on where you take it. And so too, this Jacobian is not a fixed matrix, it is a matrix that is a function of R1 and R2, just as the derivative is a function of x. Okay? Okay, so we look at this Jacobian, and the growth rate is, I tell you this, there are two growth rates that are the eigenvalues of this matrix. Now, as I just told you, this Jacobian depends on the particular point. So let us look at it for the solutions that we just found. We found trivial state 0, 0, the one with just R1, one with just R2, and one with equal R1 and R2. So for 0, 0, you can check all those R's are 0, and we get mu and mu. So we have two growth rates that are the same, mu and mu. For the one with just R1 of this magnitude, you can plug it in and see for yourself that these are the matrix becomes this, because we have no R2 and we have no R2, so we just get a diagonal matrix. So the eigenvalues are, again, obvious, they're here, but they're different. Of course, the other one has the same eigenvalues, but switched. And then finally, we do it for the mixed state, square state. We plug in these values, mu, square root of mu over a plus b, which is what we found over here for r. We plug in those values for R1 and for R2, and we get that our matrix is a scalar multiple of A, B, B, A, and the eigenvalues here are this. I think I may have a minus sign also, I'm not sure. Okay? So what does that mean? What does all this algebra mean? Well, this is illustrated on the next slide. Okay, so what it means is this. And what is this? What is this? This is now, the axes of these pictures are R1 and R2. I wrote X1, X2, R1 and R2. Meaning, for example, here, this is a solution that has 0 R2 and only R1. Meaning, it's one of these rolls that look like this, e to the IX1. That's what this point is. This point corresponds to this solution. A point here corresponds to this solution. 0, of course, corresponds to 0. And the squares are on the diagonal. They have equal magnitudes in the x1 and x2 direction. So what are all these arrows? Well, eigenvalues of the Jacobian, okay, you recall, we talked about e to the lambda t. I said this many, many times. E to the lambda t, what we said before, is lambda positive, is lambda negative? If lambda is positive, then our perturbation is growing, we're unstable. If lambda is negative, then our perturbation is decaying and we're stable. But that's the case if you have only one lambda. If you have two lambdas, you not only have eigenvalues, you also have eigenvectors. So it's not just you're growing, you're decaying. Who's growing? Who's decaying? Your space of perturbations is two-dimensional. And you can break it down, you can decompose any perturbation into sum of eigenvectors, one of which might be growing and the other one of which might be decaying. Or maybe both are growing, or maybe both are decaying. Okay? So we see here the eigenvalues. These eigenvalues are mu and mu. And what these acts, what does that, okay, the eigenvectors you can see are just unit vectors, and let me show you that here. This is, okay, this is 0. Remember, we're talking the eigenvalues of 0. And when the eigenvalues are negative, that means perturbations are decaying, meaning these arrows are pointing you right back to where you started. You try to go away, and no, it's going to die. You try and go away, no, it's going to die. So this is the eigenvectors, and the eigenvalue is negative here because this is mu negative of 0. And we see that in each case, these three things are different values of A and B. Things depend on A and B. Yeah, but in each case, mu negative, the eigenvalues and eigenvectors are negative. Now, we go back. That's only the case here that we have the same. Here we have two different eigenvalues. One is -2, the other is A minus. And what are these two directions? We're talking about the x1 rolls. So we're talking about, say, something here. This is an x1 roll. And we're talking about, do you go away or come back to x1? From these arrows, we see that in this direction, we put a perturbation in the x1 direction. Well, let's do it here. Perturbation in the x1 direction, well, we come back. We're stable to them. We come back. So the eigenvector in the x1 direction is negative. You put a perturbation in the x2 direction, well, you also come back. So these are both negative. And that, okay, so that's what's being written here. The two eigenvalues. They're negative and different. What about the squares? They have the same eigenvalues in both directions. No, excuse me. No, they don't. No. They have this one in one direction and this one in the other. And this one, as I said, I think I maybe have a sign wrong here. I think it's supposed to be plus. But so we have here the squares. In one direction, we have a negative eigenvalue, meaning we go away in this direction, the direction x1, x2, the diagonal, and we come back. That's a negative eigenvalue. But if we put on perturbation here, then we go away, a positive eigenvalue. So I've drawn in the conventions. I've drawn in the dark color the the states that are stable, meaning you go away, then you come back. And the ones that are unstable are empty circles, meaning if you go away, not in this direction, but in this direction, then you then you don't come back. Okay. So all this is determined from. Okay. So let me make sure that everybody sees not just pretty picture, but really gets this. We found the steady states. Everybody can see that. That's just algebra, just intersection of ellipses and lines. Then we linearize the equation about. We found the Jacobian, which governs the stability. And so for each one of our solutions, we found the Jacobian, which had two different eigenvalues, two eigenvalues, the same or different. And then we translated that into this picture. The positive eigenvalues were arrows going out, negative eigenvalues were arrows coming in, and the directions were the eigenvectors. Okay? So every point has two directions that it could go away in or not. And we see the answer then to the question that was posed yesterday. We see that either, depending on the coefficients A and B, either the squares are stable, or and the rolls are unstable, or the rolls are stable and the squares are unstable. Then we have another situation where they're both unstable, but we're not going to talk about that. Okay? So one or the other. And that depends on, you can see on these values of A and B. Okay, so now I have an application of this. There's a lot of words here, I don't really like words. Yeah, basically I have simulations of Marangoni convection in a square container with Marangoni convection surface tension driven. Oh, I forgot to tell you a story yesterday. We talked about Rayleigh and Bénard, and we said that although buoyancy-driven convection is called Rayleigh-Bénard convection, that what Rayleigh explained, which was buoyancy-driven convection, was not what Bénard observed. What Bénard observed turned out to be what's called Marangoni convection, and that was discovered by somebody said Pearson in the I think 50s, 60s, whatever. Another story that I was just reading just now in an article by the director of our lab, Eduardo, he was writing that because of all this, Rayleigh's paper was published during World War I, and hence there wasn't much communication, and Bénard never read Rayleigh's paper until after Rayleigh was dead, and he was sad that he didn't get to discuss it with him, because he was dead by the time he read his paper. And good have been because they were around at the same time. And that was one of the minor casualties of World War I. Okay, so here are different items. Remember, so here's the point we're making before. That's to say, if you have an eigenvector you can add. So if you have an eigenvector in this direction and an eigenvector in this direction, you don't just have two eigenvectors. You have lots of eigenvectors, but you can sum them in any way you want. In particular, you can sum them, you have equal sum, or you take 1 plus 2 or 1 minus 2, and you can, so you have at least 4 of those kind of, you really have an infinite number. But that's not true non-linearly. Non-linearly, as we said, the solutions we select are either of the kind 1 or the kind 2 or a equal superposition. You can't have any old superposition. Some of these principles also hold not only in a periodic domain, which is what we've been talking about, but also in a real square with boundaries. Now, what we did say was that the bifurcation takes place in any case. Let's see why I should do this. Yes. Even though x1 and x2 are different, everything happens depending on mu. As soon as mu is positive, that's when you form your solutions, either squares or rolls. But they're different. So you have here a principle that for mu positive, you have formed 2 solutions of different kinds. You have simultaneous bifurcation of 2 different kinds of solutions. Also, some of the same kind of solutions. You have this and this, and you not only have these squares, you have the opposite too. You can have, just 1 second. I think you can easily see that you can also have, if you've drawn them plus, minus, you can have the other kind too. Yes?
So what sets mu, like in a physical situation?
Mu, the rest of Rayleigh number, or the rest of it. It's what you're doing. It's called control parameter. You control it. I think people in phase condensed matter physics have a different name for it. They call it the, what do they call it? They don't call it the control parameter. They call it the, no, the order parameter is u, is what depends on it. Maybe they don't choose because, indeed, the phase resistance, this is it's called non-equilibrium phase, so maybe you don't normally have something to control. This is stress. Sorry?
Temperature where you are in the phase.
Where you are in the phase. Okay, so your parameter, it's u who's set for you. That's the idea, like the temperature, it's what you're varying.
This new term is like T minus TC term and the phase term.
That's right. It's T minus TC, exactly. U equals 0 is yeah, or P minus TC, right? Yes.
What do these equations look like if you write it in terms of u? Do they look like the Tuckerman equation again?
Yeah, well, that won't apply to, yes, we'll just say yes. We'll just say yes. Yeah. Yes.
And I'd like to ask a question about the switch language. So yesterday you showed us Bruce's mutability.
Yes.
And all of the
You can't do everything.
Good, and in particular, it doesn't give you the right order of things, and there's no sense in which the current review maps on
No.
to his balloon in any way, because the details of the linearities matter.
There. Oh, thank you.
No, I'm just asking.
You're asking.
Yes, I'm also complimenting, but I'm asking. Yeah, I just want you to say yes, that's true.
Yes, that's true. That's true.
No, that is, if you really care about which pattern happens in what order, then you should care about the actual equations, and not these simple models. Is that true?
Yes.
No, seriously.
No, seriously, no, I don't know what to say. I'm torn. I mean, I should say I'm a
But
very...
why are you torn?
I'm torn because as soon as I see something that's to my advantage, I'm kind of suspicious of it.
No, but it's a fact. If
well...
you're interested in predicting what happens. No, I mean, the question is because as you know, in other parts of condensed matter physics, simple models have played an important role not just in elucidating qualitative behaviors, but in actually getting the numbers right. And this is a simple model which doesn't do that. It just sort of shows you, roughly speaking.
That's quite true.
So the math is
yes, that's quite true. It does not have any quantitative correspondence. Okay, so for this simulation in a square container, you can combine the eigenvectors in different ways, and for those of you who read the notes, you will know what a transcritical bifurcation is, and this is going to come as well. I'll tell you. It's to say these eigenvectors, you can tell just by looking at them that they're going to correspond to certain kinds of bifurcations. The pitchfork I already told you about here, both ordinary pitchfork and circle pitchfork. It's where there's several branches of solutions that are equivalent. And that you can already see. The fact that you have these dashes and these lines, well, you know that you could have the opposite. You know that if you have a solution that is some multiple of this, well, then you have the opposite with the solids and the dashed, right? And same here, you could have the opposite. And in fact, you could also have, since it's a square, you could also rotate it by pi over 2 and have something that's, so you have, so this necessary, these eigenvectors, just by looking at them, you can tell that they generate many different solutions that are all equivalent. Not like the roles in the squares, like the roles in the x1 direction, the roles in the x2 direction. They're equivalent. Whatever happens to one must happen to the other. One is stable, the other has to be stable as well. So this generates a bunch of equivalent solutions. You can see it just by looking at them, and this one too. And hence, this corresponds necessarily to pitchfork bifurcations. This one, on the other hand, you cannot say that about. That is to say, you can see that if you switch the, if you rotate it, here I said you could rotate this by power 2. You rotate it, you'll get the same. You won't get a different. If you switch the dashed with the solids, you won't get something equivalent because, look, the solids are all in corners and the dashed are in the center. Maybe that's important that the solids be in the corner. Maybe that's different. Maybe if you were to switch solid and dash, you would get something that wasn't a solution or was a different kind of solution. Unlike here, where you can say, well, who cares if the solid is up and the dashed are down or the other way around, because there's no difference between up and down. But there is a difference between center and corner. That there is. So you can tell from this, you can see that you will not have a solution that is equivalent. You will have a solution that corresponds to this eigenvector, yes, but there is no obvious twin that's equivalent. Yes?
What do the dashes and solid lines mean?
They mean hot fluid and cold fluid, say, or they mean fluid coming up and fluid coming up.
So
they mean positive and negative.
Down from the top.
Yes, yes. Or hot and cold. Okay? So just by looking at these pictures, you can tell what kind of bifurcation it is. And now, here is the actual computed bifurcation diagram for this problem. Okay, and actually, okay, so I want to show you something, something striking here. Here, I mean, it's the same thing that I've been telling you. This is a pitchfork bifurcation, and let's look at what it looks like. It looks like a, the dark roll and the dash. By now, it's no longer symmetric, but you can bet that there's another solution that looks just the same, but that has dashed and dark, or another one where the dash has a bulge instead of the, you can see that there's at least 4 solutions. I think there are exactly 4 solutions that are dynamically equivalent coming out from here. So they've just been drawn by one branch. Here is something that came out at the same pitchfork bifurcation over here. And what does it look like? It looks diagonal. So that's like the squares. You have this one, I mean, when it first came out, it looked this diagonal was straight. So here you have also a bunch, and of course you can bet that there are other solutions that are equivalent to that. For example, you can turn the dash to solids. You could also rotate it by pi over 2 and have this diagonal instead. So you know that there are 4 solutions corresponding to this, just as there are 4 solutions corresponding to this. These 4 solutions, they're all equivalent to each other. These are all equivalent to each other, but they are not equivalent. This set is not equivalent to that one. They have different properties. Having a division around the diagonal is different from having a division here in a square box. And you can see they have different properties. Another convention that I didn't tell you before, for the bifurcation diagrams, just as now I told you over here that the convention is that the solid circles are stable states and the empty ones are unstable states. When you draw branches of solutions, and that's what this is. These are branches of solutions. These are solutions as a function of the Marangoni number, proportional temperature difference, like the Rayleigh number. The dashed corresponds to unstable, and the solid corresponds to stable. So you can see they're different. These are unstable, these are stable. So this is a case where the rolls, if you wish, are stable, and the squares, although it's not squares, this is what I mean is the superposition of 2 rolls. These are unstable. And then you have a bunch of other bifurcations, and again, okay, this is a transcritical bifurcation, and that's what I was just telling you. The ones that look like this are transcritical because they don't have partners that look just like them. Partners that are dynamically equivalent or different, a whole bunch of other diagrams. Okay, so all of these, this is a real numerical simulation with real equations. Just one second. And, so of course you can't indeed predict those photographical symmetry principles or anything else, what is going to be quantitatively. But all of these bifurcations follow these principles that come from logic and from math that tell you that this has to be a pitchfork bifurcation, that there are equivalent branches, that this one has to be transcritical, and all the rest. Yes?
So in the lower half of this diagram, kind of to the right, there's, somewhere between those 2 pictures on the bottom, it's just like tons of instability. So
yes.
What happens if you end up in that picture? Where do you go?
Oh, okay.
Anywhere in here.
You go, where you go is to one of the stable branches. You must go to one of these dark lines.
Yeah,
In fact, other branches exist is not relevant. In fact, here in this region, you go here, because this is the only stable solution.
Okay, do you pass through like a different
No.
type of picture? Like, do
No,
you change
no.
pictures on your way to the stable?
Well, it depends. Okay, everything depends on your initial condition. If you put in an initial condition that looks a lot like the final condition, you won't pass through anything else. If you put in an initial condition that looks a lot like one of these unstable guys, you'll probably go pretty near one of them before moving. Sorry?
Random initial.
If you put in random initial condition, I think you'll most likely get, it depends on the different, it depends on the initial condition, and it depends also on the relative sizes of all these eigenvalues. Because the eigenvalues tell you how fast things go. So you put on something that has very negative eigenvalue, that part of the initial condition will immediately be damped out and go to zero. If you have something that has one negative eigenvalue that is, excuse me, a positive. If you have a negative eigenvalue which is not very negative, then you'll stay there. Then it'll take you a long time to get there. So it depends. You take an initial condition, and it is a superposition of eigenvectors, and each one grows at its own eigenvalue rate, and
Thank you.
it won't necessarily do something complicated.
Okay.
It doesn't have to.
Okay.
Yes.
What is the verdict of? So what is
That is to say the temperature at some point is what's called in transit phase uses an order parameter. It can be anything. Basically, you use anything along this, and you will get the qualitatively similar, quantitatively identical bifurcation diagram. It's the temperature at one point, or the velocity at one point, or the heat transfer, or people tend to use global quantities for this, but that's not so good because it doesn't distinguish between symmetrically related conditions. I tend to take just the value of temperature at some point, just some random thing. But the bifurcation diagram is indifferent to which you choose.
Okay, so it's not like some sort of...
Well, the temperature at one point is...
It's arbitrary.
That's arbitrary, that's right. Arbitrary it is, just so. Yes.
Are these have been...
I'm sorry, just one second. It's a one-dimensional projection of this vector field. Yes.
A lot of good experimental sort of verification of these kind of images and pictures?
No. And this brings me to a philosophical point. I believe that something like this needs no experimental verification. That is to say, people laugh and say, oh, you're a numericist. That is to say, there are plenty of things that need experiments. Turbulence, funny geometries need to, you'll have some, no, you're not saying that. Okay. But the Navier-Stokes equations, the Boussinesq equations, these equations have been tested.
But that's not true. So how do you say this? You started out saying, so let me just summarize the beginning of the lecture. You said, this is what you said. You said, the state of theory is that you can study the competition between rolls and squares and rolls, but you can't do rolls and squares and hexagons. So the only way you know what it does is by doing the experiment.
The experiment.
And then you can make a theory of the experiment.
No. This is a numerical simulation, and it is just as good as experiment. It's better than experiment. It's a perfect experiment. This is in a square box.
I had a very interesting discussion. I had a very interesting discussion with Gunter Ahlers on exactly this matter. So what we wrote in the paper is that we did numerical simulations, and what we wrote that this could be a benchmark for experiments to see whether the boundary conditions, constant temperature, and so on, whether they are probably fulfilled. And he was just furious about it. We were good friends, but he was very, very upset. I mean, it's a kind of a philosophical point of view.
Yes, okay, but wait a minute. Am I supposed to think that because Ahlers was upset that I'm wrong? Or what?
No,
What are you trying to
it's a
say?
very philosophical question. I mean, what's the role of experiment, what's the role of numerics?
No. I disagree.
It's purely, it's basically, it comes back to the...
Right, no. I am not talking philosophy of numeric versus experiment versus simulation. I am talking about Navier-Stokes or Boussinesq at small Rayleigh number, at small Reynolds number. I'm not talking about the general. Of course, there's a lot of places where we don't know the equations. There's a lot of places where you need to compare. There's a lot of, but I'm saying for things like this, we've been simulating for 40 years. We've been doing experiments for 40 years. This is done.
I mean, in this discussion, I was very much on your side. I mean, I had the same view.
I'm not saying no experiments every.
I think also Michael has a very different view. I mean, it's more the Aristotelian view, whereas your view is the Platonic view. These are the equations, and this is how nature, if experiment is properly done, better behaves.
Yes.
Otherwise, you experimentalists screw up.
Yes, that's right.
Yeah, I mean, I defended the same point of view.
Oh, okay,
but I mean, many experimentalists will be very much mad at you.
I know, they are. But I believe they are not making this fine distinction. That not all experiments are equal. For example, that to really know the trajectory of a ball as it goes down, I have to do the experiment? Of course not. This is known physics. You know that you
That's
know.
because that experiment was done.
I agree. Experiments of miracle convection have never been done, and it's not as if it was codes were born full blown, you know, and everybody already. You know, this has been done. This has been done. It's been done. Now you can look at the code, and you do not need to verify it anymore, and you can run this.
So may I make a comment?
It's just like dropping the ball.
May I make a comment? Well, you should go on and do it, but I really should take one more comment. Which is that the reason that it's interesting to me experiment, and I'm not advocating, by the way, that anyone in the room should go and study the bifurcation diagram of man going. I'm not advocating that, but the reason that you do an experiment is because it might show something different than what you expected.
Indeed.
In which case you actually discover.
Indeed.
And so the problem with your point of view, no, the problem with your point of view, and your point of view, both of your point of view, is that basically, if that were the way it is, no one would ever discover anything, because everything, I mean, it's just.
No, there are plenty of things that are a little more murky than this. I mean, you could say the same about the ball. If you keep drawing, you must
It's too murky, it's hard to
push to
discover
the
things.
extreme. Look, if you take a ball, indeed, perhaps one time you drop the ball and it's going to go the other way, and you would discover something very interesting. Are you really going to spend your time doing that?
No, I think that we all make choices in life about what experiment or whatever to do, and those choices are bets, and I just would not urge, I mean, I personally would not do this experiment.
Right.
I also agree that you won't discover
There's a
something,
continuum.
but I may be wrong. It's possible, and so, you know.
So I do not want this thing of experiment versus simulate. There's a whole continuum, and things that are very well known and very well simulated do not need.
I mean, Laura, you spent 10 minutes yesterday complaining about the lack of the spiral defect chaos. Remember that?
Yes.
What about that? I mean, you know, who the hell? You shouldn't be doing, I mean, pattern formation and reservoir convection.
That's true, it's true. But they did it in a big container.
But small container, big container, what's the difference? No, I just, the logical extension, there's no one would ever discover it.
Well, that's true, but there's many things that taken to the extreme are stupid. I don't advocate taking my position to the extreme.
Well, but small versus big container is hardly extreme.
No, I know. But the extreme point is no one would ever. Oh, all right. As you say, lunchtime. Okay. All right. Now, okay. So now my final thing I wanted to say was, it turns out. Remember last time I showed you these. And I'm going to show you. It's not that I had all of this. My windows are closed, so you can't tell. But it's not that. It was that I was showing it in the wrong place. If I show it on the web, then these things work fine. If you try to use display to show my GIFs, and that's why it was slow. Okay, so these are my simulations of convection. This is the traveling wave, and then this is
Convection, I mean, this is Delaware, right?
no, this is convection. The container isn't rotating. This is one of the miracles of bifurcation theory. Here, the same experimental parameters.
I agree that it's the same for the equation-wise, but I mean, wasn't the solidus rotating, or?
No, that's the temperature. The temperature is rotating. You get, for these parameter values, too bad you weren't in my class yesterday. You would have learned so much. Yes. Oh.
Then I would get this. Very nice hike, so.
Hi. And you're going to tell me you don't have tall mountains in your native Holland?
No.
Well, that's the first time I ever heard that. That's scandalous. Okay, so this is simulations of convection. For those who weren't here yesterday, simulations of convection. This is right in the mid-plane, which you can see is the temperature, heated from below, cooled from above. There is a transition, spontaneous, no temperature, nothing time-dependent or oscillatory is imposed. And this is the solution. This is a solution. I mean, it's by no means standard to have a solution like this in convection, but it's not unknown either. So you have the standing wave, and you remember this is a standing wave because the nodal lines stay in the same place. If I leave my finger here, you see maximum, minimum, right? And the same thing viewed from the side. Again, the nodal lines stay in the same place, right? And it also has the solutions which are traveling waves like this. And here, you can see this is just the temperature. This is not the container that's doing this. And this doesn't have nodal lines. It's a traveling wave. And this one is the traveling wave seen from the side. And again, this is a temperature. It's not the side because the side has to have the same temperature. It is maybe 3/4 of the way in, so that's a hot spot, there's a cold spot. Okay, so those are solutions to the equations of convection with no time, it's time-dependent equations, but no time-dependent forcing. And I said, you get these four, and somebody asked me, are they both stable? And I said, no, they're not. For the same reason that we just said. Either one is stable or the other is stable. But they were, and this goes back to your question here, it depends, what you might see in experiment or in simulation, it depends on your initial condition, and if your unstable solution is unstable, but it is not very unstable, if some eigenvalue is positive, but it's not very positive, then we'll see it for a while. So that, indeed, we know theoretically, after we were able to learn this theory, we saw that these were, these are the standing waves, these are the traveling waves, and either the traveling waves are stable. This is bifurcation diagram where something arbitrary in answer to yes, is drawn as a function of mu. Either the traveling waves are stable or the standing waves are stable, but not both. And it turned out that if we waited long enough, the standing waves lost to the traveling waves. Okay, so almost. Okay, this is, as you notice, 16 out of 37. Who thinks I can finish? I know this time I can't stay extra. Hexagons. Hexagons are a superposition of 3 different types. You got K1x, you got K2x, you got K3x, where K1, K2, K3 are separated by 120 degrees. Now, what's remarkable about the geometry and algebra meet, as in all the best mathematics, this allows quadratic terms in the equation. Why is that? You recall here, when I gave you this equation here, I said that this term here corresponds to e to the ix1 times the conjugate, the minus ix1, times e to the ix1, and that gave us e to the ix1 again. So this whole equation was in terms of e to the ix1. And I said nothing else could do that. You couldn't do e to the ix1 times e to the ix1. That would give you 2ix1. And so that would have the same functional form. So you could not have any quadratic terms here. And basically that is because by taking a wave vector like this plus a wave vector like this, you will never get back to something that is good. But that's not true of these hexagons. In the hexagons, we have that K1 plus K2 plus K3 equals 0. And therefore, if we multiply e to the minus K2, e to the minus ik2x, e to the minus ik3x, we get e to the minus we get e to the ik1x. So we can put terms like z2, z3 bar into our evolution equation for z1. And the same holds for all of them. So our equations are, they're the same, for z1, z2, z3, they're all permutations of each other, there's symmetry between 1, 2, and 3. But each one gets to have the quadratic term, which involves the other two guys. z2, z3 in the z1 equation, z3, z1 in the z2 equation. Okay, so from this picture with the vectors, we then get this algebra that allows the quadratic terms. We're getting back to those terms in the Swift-Hornberg equation. We then do, now we can do some algebra that I'm going to go through this fast. I don't really expect you to follow this. It's in the notes, although perhaps not in the best order. Let us, now this time, instead of making z into x, as we did before by just choice of phase, we can't do that anymore, because we could do it for the other one because there are 2 phases. There's a phase in x and phase 1. But here we have 3 phases, and we can't make them all 0. We can choose an origin in x, and we can choose an origin y, but we have 3, so we can't. So let us instead do the next best thing. Let us write z as r e to the I theta, and let us now seek solutions. Okay, you can see that you have solutions that are all z1. If you take these terms are 0, this term is 0, and you get z1 equals square root of mu over b. You have solutions that are all z2. So you can have rolls that are like this, you can have rolls that are like this, and you can have rolls that are like this. All those are allowed. Let us look for solutions where R1, R2, R3 are all non-zero and all equal. So you plug in R e to the I phi, and you do all this. You separate the equation, evolution equation for R, the evolution equation for phi, and what you learn is that there's 2 possibilities for these phase angles here. Either this, okay. These both, you're looking for steady state, so these things have to be 0. So phi1 plus phi2 plus phi3 has to be either 0 or pi, right? And then depending on whether it's 0 or pi, you will get plus 1 or minus 1 here. So you get 2 different solutions, okay? And all that's written down. And The point here is that you have two kinds of hexagons, one with a 0 and one with a pi, and you can see they look different. You can draw this, and now the third set of lines, you can draw them through the intersections of this and this, or you can draw them halfway through, which is there. So those are the two kinds of hexagons, and they are not equivalent. So knowing this, we already know that hexagons bifurcate transcritically. This is not equivalent to this. You have two branches. Transcritical bifurcation looks like this. You have one, okay, so this is the order parameter, this is the arbitrary thing. I'll write arm here. This is mu. We have one branch here, and then we have another one that may be someplace else, but we don't have two equivalent branches, unlike the pitchfork, where we have this or this which are. And if you do all the calculations, you find the rows, you find the hexagons, you also find a set of things called rectangles, where two of the r's are equal, the third one is, no, there are two, anyway, you find this, and of course we're not going to go through this because we don't have time. Okay, so this is the bifurcation diagram for the meaning. These are the steady states. This is the arbitrary thing. It's some measure that says it's as a function of mu. You have the trivial state, you have the up hexagons, the down hexagons, you have the rows. We have, of course, many different kinds of rows because we could have them this way, or this way, or this way, but we're not going to draw them 3 times. We could also change the phase, but we're not going to draw them 1 times. We have these other bifurcations where you lose stability, where you gain stability. Necessarily, this may not be obvious, when you create new states, or when two states intersect, and not just in the arbitrary projection, but when they really intersect, then there's a change in stability. And that is not obvious, but it is true. And those of you who know bifurcation theory know that, and the other ones will learn it sometime. Okay, so this is the diagram for the hexagonal lattice. And what was I going to say? There. Okay, so then here's some illustrations. This is Michael. This is an illustration. Okay, this is with my student. This is simulations of the Faraday experiment, and because you cannot just because you can't decide which. No, it doesn't. He tailored the box to either contain squares or hexagons by these measurements, and he then produced either squares, that square type box, or hexagons. It may not be obvious that these are hexagons. And this nice looks like a volcano, but let me show you now movies. Okay, this is a square movie. The Faraday is a time-dependent problem. This is unlike the convection problem that I talked about. This here, Faraday, you may recall when we talked about it, is where you shake the blue light. So this time dependence is put in. It's not something that comes out of the problem. It's in. And then in this, you can also get hexagons, and here's a movie of that. Okay. Anybody want to see those movies again? No? Okay, and here are pictures that have more of details of the velocity field. Here you see that it looks kind of like a volcano. This doesn't, and this illustrates the US, of course. Oh no, it doesn't. Look, simulations show this detail. The theory said you might have squares or hexagons. It's mathematical theory. It's very general. But if we had to do a real simulation, not in front of a real simulation, to see that we had a kind of volcano thing here, that we had a grounded tip here, all that kind of thing. Right, so that illustrates what you were saying about.
But I mean, just out of curiosity, if you were to do the theory of these parameters, would squares be stable?
It turns out that for this, what you do is, as you increase, this is the shaking amplitude, it's the bifurcation parameter. And for low shaking, first you get squares, and for higher shaking, you get hexagons.
But you get hexagons because of the instability of squares, or do hexagons just become more? Because since you can't compute squares against hexagons, you don't know if squares go unstable. That is, do squares go unstable right when hexagons become stable?
Right, you're right.
No, but you should be able to know that by simply studying the stability of squares and hexagons. Which you can do. At least, but you can only study the stability of rows. I see. So you don't know that.
I don't know that, but I can do it numerically though, and maybe I should. No, I can't because I don't have the right kind of box. I don't have a box that accommodates for.
But isn't it terrible?
Yeah, you mean it's a pretty question that's not answered.
Yeah,
Yes, yes, indeed. It is surprising. It is surprising.
I mean, it's just so simple.
It is indeed. It is indeed. It's possible more is known about this than I think, but I think that's true. I think it is a basic question that is not answered.
No, it just might be that the squares and hexagons are both stable, but
In this experiment, no. For a certain shaking, you get squares, and then a higher shaking, you get
See,
hexagons.
the problem is they can't study the stability of squares without, you can only study the stability of squares where I'm destabilizing two rolls. But if rolls are unstable and squares were stable, you can't, I mean, there's-
But
you
the
really can't
experiment,
form
okay, but
Sure, you can do the simulation, but.
no, but but here, okay, indeed, roll it back to experiment simulation. We're restricted by our code to just do a single box. Although these look like large domains, that's a fake because they're just periodically repeated. So we do a single, whereas the experiments that we were trying to reproduce, they did a big box. So they saw the transition from the squares to the hexagons because they did a big box.
So it's good that they did the experiment.
I repeat, I was not making an all-purpose philosophical argument. I was saying don't do stupid experiments. And too many people think that if you do a simulation of really good argument in some little box, that is something new. It is just as not new as dropping a ball. Of course you should do experiments, but not stupid experiments. But you agree with that, of course.
Yeah, I do that.
You just wanted to yes, right. At least everybody's awake. Okay, so these are more pictures of the hexagon. You can see how pretty it is. It's not just hexagons. They're rounded here. They have these bumps. They have nice qualitative details. Okay. Now, in the 7 minutes that are left, I want to talk about instabilities of roll patterns. You remember the Busa balloon from last time. You remember Busa, this very Busa that I mentioned several times. These are rolls in convection. And these are calculated, the instabilities that are formed, the cross roll, the knot, skew varicose, zigzag, and so on. And you recall that I showed these pictures that, amazingly enough, are in a granular, in sand, in a vibrated granular. It has the same instabilities, showing that these instabilities are not just a particular property of convection, but they're general things, just like the theory of squares versus hexagons. These instabilities are general. Now, unfortunately, of course, I cannot go through the details. I would have liked to. Eckhouse instability is when you, I'm sorry, here's more. Also in these granular layers, Sweeney's lab, 1998, you see squares, and you see rolls, and you see hexagons. And this is one kind of hexagon, the up hexagons and the down hexagons. See, they're not equivalent. Here you see some kind of instability, here you see roll, just like what you saw before the simulation. And this is sand. Shaken sand acts the same as Swift-Holmberg, acts the same as fluid heated from below. So you can see it's really very general, general theory behind all this. Yes?
The sand shaken from below.
This sand is shaken, that's right. It bounces. Okay, but that, as I said yesterday, I was looking for pictures from convection for this, but because the research on convection was for pre-web, it is not, it's not easy to find on the web. Okay, so from the Swift-Holmberg equation, one goes to the Newell-Whitehead-Segura equation, which might look similar to you, but it's kind of different. And I would like to do this in detail, but I cannot. Of course, we don't have time. But you will find it in the notes. And we can calculate the Eckhouse instability, and that's when we perturb something that looks like this with something that looks like this, and we can calculate easily the find the eigenvalues. What you meant? Sorry, because I'm going too fast. That one, no. There was something funny. What was funny?
The slide just before was a sea of differential equations.
Oh, this,
and
yes, right.
We don't need to see
Yes,
it.
yes,
Okay.
yes. That's right, that's right. No, okay. I'm just saying it's possible to do, and it's not just possible. This is easy math. Look. Look, 2 by 2 matrices. Come on, it's 2 by 2 matrices, and you know, and this is just you know, multiplication. It is nothing fancy. Okay, and we can do the same for the. Okay, what we find is for the Eckhouse instability. This is the marginal curve, the same one I showed you before, and we find that it is the primary bifurcation from what I showed you before, and then the secondary bifurcations are Eckhouse. And then the zigzag, okay, this is, okay, again, I don't have time to show you. Let me show you then, instead of doing the algebra, I would like you to know that this algebra is easy, you all can do it. I'm talking about 2 by 2 matrices. If you know how to diagonalize a 2 by 2 matrix, you can do all this. But instead, I will show you the wonderful simulations from my crosses applet, and here they are. Okay. You see you have 2 sets of rolls with different wave vectors, meaning these are, this one is bigger, so that means the wavelength is smaller here. So these are a little more crowded than that, okay? And so let's start these simulations. Let's start them at the same time, like a race. Okay, ready, go.
Who's ahead?
Ah, did you see what happened? Okay, let's do it again. Okay, the point of Eckhouse instability is it has some wavelength. This has to do with what you said before. It's been prepared with some wavelength that it doesn't really like. It's okay with it, kind of. It's got an eigenvalue which is positive and not very positive. So it can stay there for a while. Okay, so let's do that. Okay, and so so it has wavelength that it doesn't like so much. And so it changed it, you see? It's changing it. We can also look in the Fourier transform space, like as before. Fourier transform space. Okay, so notice this is the Fourier. This is just stripes. So there's just the magnitude of Q that matters. This is 0, and this is plus Q and minus Q because complex conjugates. So plus Q minus Q. You can see they're slightly different. Do you see that? Okay. And we don't have a whole fog of things because it's really just regular stripes, but just with the wrong wavelength. So let's see what happens in the Fourier space. So in time it takes a while. Yes, that's a good idea. Yes. Okay. And then it jumps, you see? It widens and then it jumps. It widens as it becomes unstable to those eigenvectors that are you got Q plus Kx, you got Q minus Kx. It becomes, sometimes it's called the side band instability because it's on the side. Okay? Okay, so that's one simulation of Eckhouse instability. And another one is here in a 2D domain. No, it's yes, okay, this isn't a 2D, this is in a more restricted domain as before, this is in a larger domain. Okay, let's start them. This is going to do as before, see? Right, it already went to its final one. But this one, look what it's going to do. It's taking a while. It has trouble because those roles are really well established. It has a whole domain in which to have those roles. And you see, it didn't do it all at once. It formed it from there, and then it had to kind of propagate and go all over the place. So it took its action in different places at different times. And now it's trying to straighten itself out to be a role. So it's not, this part is going to take a little while, just as you saw before, kind of bent. Okay, we can look at the whole thing in Fourier space again. So we did that here. This one, Fourier space. You see, it's not quite ready yet. There should be just 2 Qs. Right? Okay. Okay, now let's stop, reset, and look at the whole thing in Fourier space. So remember, it has a wrong wave number. There, it made its wave. Now this one now, it's going to take a while. Let's see what it looks like. You see what it's doing? It has all these different things. It always stays complex conjugate because it has to be real. You see what it has these defects? Those defects are seen by the fact this is the main direction. There's this one to get rid of too. You see, this is the main direction that has to get rid of stuff like that. These defects here have to go away. They're getting there. Two directions. You see one direction like this and one direction like that. But now it's going to take a while, probably. Why? Is this not on? What's wrong with this? Well,
Microranges, it goes you a lot over time.
Good point. Zigzag instability is the last thing I have to show. Right. Good point. Okay. Let's just hold it last through this. This is the zigzag instability. Also has the wrong wave number. Well, look what it's going to do. It's going to make a zigzag. Yes, that's a very good point. That's right. Someplace it gets. Yeah. But you guys don't know this, because I saw this yesterday when I was learning. Also out of electricity by the end of these plugs don't work.
This is the advantage of getting talks on platforms.
Yeah, true. So you see the zigzag instability, it has the wrong wave number. Remember the booster balloon? That's when it has the wrong wave number, but it's outside of that balloon. It's not happy with the wave number that it had, but it's finding this way to get to a better wave number. Oh, I know, I can make you go faster here. Just stop. Go faster. Here, 50. Is it going faster? No, just on the screen. Okay, so I can take, anyway, this is my last transplantation, so I can take questions. We should try.
In the sand experiments, the granular experiments, you've got light and dark patterns. Is that because it's a bigranular layer, so you've got two different types of grain?
I'm sorry, say, what's your first word?
No, I think it's one. I think it's straight and
But, I'm sorry, what is your question?
I was just wondering what...
No, it is one type of grain, but why did you want it to be two?
So I was wondering how you got light and dark patterns from it.
Light and dark. How are they light and dark?
in the granular, in the sand.
No, no, I
grains are
know what
light
you're
in
talking
the
about, but how they light and dark.
Okay.
No, sand and not sand.
Oh, yeah, yeah, sand.
Ah, okay, there, that's it.
Other questions, comments?
So in this three-point equation, you come up with answer of square and hexagon. Can you predict the pattern economic answer?
I think there's many parts of that
I
question.
think the answer is no,
There, the answer is no.
That's the problem.
What's the question?
right? No, you can't compete squares
You
against
can't compete
hexagons.
squares and
You
hexagons.
can't even compete squares against hexagons.
In fact, the
It's stupid.
Tuckerman equation, as far as I can see, does not produce squares. Right, you haven't seen the squares, you've only seen rolls and hexagons. I don't think it produces squares, so you certainly can't see the content of the squares, I think.
Yeah, no, it's an embarrassment. No, for all of us, it's
So
embarrassing.
you mean we start with initial and calculation, cannot do it.
No, you have to run the computer, and then you can predict it after the computer's done.
Think.
See, there's so
I
many.
mean, I'm not, okay, I'm a big consumer of this theory, but I'm not a producer of theory. I'm a producer of simulations and interpreter using bifurcation theory. But there are people who really know
No, but that's
this.
not fair, right? I mean, come on, if this problem were solved, we would know.
Yes, no, I agree.
We would know.
Yes, yes, no,
And this is a glaring
but they
fault.
might know more details about in what sense it's not solved.
No, it's not solved, because we don't know the answer, so.
Does the symmetry of the problem select certain type of pattern?
No, I mean, it's simply wrong. We're talking about homogeneous, the only thing that we've been looking at theoretically, look what it did. See, it's forming rolls now. It did, you see now eventually it's going to settle down to rolls. It's supposed to be homogeneous in space with no, the symmetry of the domain is Euclidean symmetry, meaning all translations, all rotations, every point in space is the same.
The symmetry of the governing equation.
The governing equations have that same.
Like if you have like latitude to the port, it might allow only like.
Well, that's what you impose, yes, that's what we did to find the squares. We imposed a solution of the form that could take on the squares. The hexagons, we imposed the types of solutions that could take on, we put down a square grid or hexagonal grid.
Okay, one last question.
Isn't that a problem in itself though? Because not only can we not decide which of the forms is going to happen, but also by assuming like that there's only two cardinal directions or three, we've restricted, like there might be a form with five cardinal directions that we don't even consider, and which might come up in a certain case.
Well, yes and no. Not many things can tile the plane, but
But there's no
but there's no,
requirement.
that's right. There's a lot. That's right. There is no agreement on. And in any case, you have things like this. That's not captured by theory per se, although they've tried to capture by phase diffusion.
No, but I mean, this is why all things are disaster. Let's not do that.
But maybe it's more advanced than all that. I don't know. I would hate for
You think there's
people to be
something you don't
misled by. I know that there's a lot that I don't know. There's a lot that I don't know. I don't think there's one big fact that I don't know, but I think I can.
I mean, so it may be right, but I would have thought that it's playing out, if you don't know that. Because this is a pretty,
I know that there is no general split analysis for squares versus hexagons. That they're done, each is done on its own lives. I know that.
That's still the case.
But still, there might be a lot more known than merely saying we don't know. There might be all kinds of partial answers and partial. But I, this.
Okay, so I propose we clap. No, let's.